Hello everybody. Thank you for joining us today for this webcast on RF Front End module for cell phones. You are part of the 350 people worldwide who have registered to attend this webcast, which is powered by Yole Développement and System Plus Consulting. My name is David Jordan and I am part of Yole Développement sales support team in France. Before we get started with the webcast, I would like to give you some practical information. First, you have the possibility during all the webcasts to submit questions. In order to do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions today as time permits. However, for the remaining questions, we will make a follow-up via email after the webcast. Concerning the material that will be shown during the webcast, please note that the presentation is available and downloadable in the material sections. Anyway, you will also receive an email after the webcast with a link to the recorded session. So today, Yole Développement and System Plus Consulting will share their analysis so you can better understand the strategy, business, and technology trends that impact the RF industry. This webcast will last about 1 hour. So first, let's start with Stéphane Elisabeth from System Plus Consulting. He is Senior Cost Engineer. He will present a technology review of front-end components in cell phone and an overview of the current integration solution. Stéphane, the floor is yours.
So, hi everyone. I'm Stéphane Elisabeth, Cost Engineer at System Plus Consulting, and I'm in charge of RF and advanced packaging, and I will talk about front-end modules technology for consumer application. So to begin with, I will talk about the entire RF system in mobile phone. The RF module system that allows communication is in well-known smartphone is actually composed by several blocks. All system has power amplifier, filter to provide best SNR on selected frequency band, antenna switch to provide communication on several frequency band, antenna tuning to match the impedance of the antenna according to the frequency. And depending on the constructor choice, all blocks of the diagram can be integrated in one module or in discrete mode. But several challenges occurs when we want to integrate all in one. So power management, thermal dissipation, electromagnetic interference, etc. So finally, the solution could be relatively expensive. My presentation will focus on the front-end integration, explaining, for example, why we have such a difference between Xiaomi solution, for example, in a Mi 5 model, and in Apple iPhone 7 Plus model. So, in the market of the front-end module, we can find several actors depending on the frequency band, the performance of the product, and the affinity between the seller and the buyer. Usually, Skyworks provides solution to Huawei, Murata and Broadcom supply Samsung, and Apple sourced its FEM from Broadcom and Qorvo. In fact, the solution has to cover the whole communication mobile spectrum from GSM band to frequency close to Wi-Fi band. And to do that, we have to use several technologies. For example, for filter, we have SAW filter and BAW filter. And the choice of the supplier is based on the complete smartphone design, discrete or fully integrated, the cost of the modules, and the performance required by the buyer. So to illustrate one criteria, for example, the performance, in the filter we have two technology. And depending on the performance we want, we will choose one of them. For example, depending on the frequency, SAW and BAW filter can be hard competitor. Currently, SAW filter are used at low frequency. This technology is based on acoustic wave traveling on the surface of the piezoelectric substrate. And the distance between the transducer is inversely proportional to the frequency. And for high frequency, interference issue can occur. And for many years, BAW filter became a better choice. The acoustic wave will travel in the piezoelectric layer, depositing on acoustic reflector. So technically, the limit of this technology is the thickness of the piezoelectric. So the integration could be better in high frequency. After, let's talk about the FEM, the module integration. For the design choice, we can find several choices in the market, from the more expensive and more integrated solution to discrete implementation. For example, Apple used Broadcom and Qorvo in its latest flagship, the iPhone 7 Plus. Avago for the mid and high band, and Qorvo for the low band. One version of the smartphone could work all around the world. Samsung use a different business model. We have 3 different versions of the Galaxy S7 that we can find all around the world. All 3 show different FEM depending on the microprocessor that it's used. USA and Southern Asia, a version uses Qualcomm Snapdragon, so they use Qorvo high-band FEM. And in the European version, using the Samsung in-house processor, the Exynos 8, we found Broadcom FEM for the high band. For the European version, Samsung could integrate Qorvo's FEM, but here we think that the second criteria as cost of the filter became the decisive parameter. So the next 3 companies are oriented to low-cost model, which correspond to discrete implementation of the front-end system. For example, from the all-in-one Sky1 solution from Skyworks in the Huawei P9 and P10 to a single PAM and several discrete components for the Xiaomi Mi 5. And we have saw that for the LG G5 we found an average solution between all integrated and discrete implementation. So at System Plus Consulting, we have published several reports on advanced feature, packaging, and FEM technology in RF mobile application. And to begin, we will go through a front-end system smartphone comparison integration. After, we will see several modules solution, and we will finish on what could bring 4G plus and 5G on technologies and costing. So first, depending on the business model of the original equipment manufacturer, the coverage of the band spectrum could affect the system implementation choice. For example, one model working all around the world brings a compatibility with all LTE band, which results in less than 25 bands supported. Whereas some OEM focus their application on one word area, so it resulting in less than 10 band covered and a freedom in PCB space. So in fact, we found only full integrated solution in expensive smartphone, from OEM like Apple and Samsung. Low-cost customers consider PAM coupled with discrete filter. One interesting fact is that the position of Samsung, which has different model depending on all around the world, leading to less band to covered and all integrated solution with less filter, resulting in lower cost. So after we will see two front-end solutions. First, we will focus on the Huawei P9 and P10 system integration, and where we have the technology solution from Skyworks called Sky1 2.0. This solution comprises 3 FEM covering the low, mid, and high band. And thanks to its SAW technology, Skyworks managed to cover the low and mid band with only one SAW filter with metal sealing in the mid band component to avoid electromagnetic interference. But for the high band solution, SAW couldn't compete with both filter, which has led Skyworks to outsource the duplexer, the band 7 duplexer to Taiyuan. As the frequency application increase, we can see that in the area repartition, the blank space required more and more space to avoid interferences. In the second application, we will see the Apple iPhone 7 Plus solution, which has a fully integrated solution from 2 suppliers, Broadcom and Qorvo. And surprisingly, Qorvo has been selected to provide low band filter. All in a SAW filter application, but knowing the performances of its low drift solution, we think that the choice is understandable. With less than 32% of blank space, the solution has a very low form factor. On the mid and high band, Broadcom relies on its F-bar bow filter and microcap packaging technology. So what about toward 4G Plus and 5G? First of all, in the past year, System Plus Consulting has conducted 2 reverse costing on Broadcom FEM modules. We analyzed the FEM from iPhone 6s Plus and the Samsung S7. We also analyzed the latest FEM from Broadcom in the iPhone 7 Plus, and we found that Broadcom has gained the Apple approval for the use of the scan jump dot piezoelectric to enhance the F-bar performance. We have shown that by TEM observation that the scan jump dot aluminum nitride is well mastered with high crystallinity, high C-axis orientation, and very smooth columnar structure, which confirm that it's in the next few years this technology could be applied for LN-based filter in 4G Plus and 5G application. The other challenges bring with 5G Plus and 4G Plus and 5G could be the thermal management. In high band applications, for example, cost-expensive solutions, like metal sealing, has been still privileged, and this type of package could take more than 70% of the cost for example, in band 7 duplexer from Yole. And one solution that could take place in the market, could be the use of glass interposer, for example, resulting in the Qualcomm project with Corning, that studied the possibility of integrated passive and active component through glass interposer. And this approach could bring, using cost-effective manufacturing technology from Corning, this glass interposer in 5 components, solving the heat dissipation, the integration of the IPD, and the cost issue. So, thank you.
Thank you very much, Stéphane, for this interesting overview. So once again, do not hesitate to ask questions using the Q&A button, and we'll try to answer some of the questions at the end of the session. Now let's continue the webcast with some market perspective that will be added to this technology overview. Claire Troadec is leading the RF activity within Yole Développement, and she will now present you how these RF front-end components and modules are expected to evolve with 4G plus and 5G. Claire, it's your turn.
Okay, thank you everyone. Good morning or good afternoon, depending where you're located. So it's a pleasure to have you here. So we've had a nice introduction by Stéphane to really look at what we have today in our smartphone. And we do see different choices, different technology choices from the system integrators. So indeed now we are going to have some kind of market outlook and really look more into the ecosystem of these different RF industries. Okay, so let's start. Just as an introduction, before we really go into serious technology topics, let's have a look really at the global mobile data traffic worldwide, and you will see with this picture that, for example, last year in 2016, so there's a huge amount, of course, of global data traffic. And you will see that smartphone still is increasing and remains the main data usage system that is used to do this data traffic. So it was representing around 70% of the data traffic last year, and it will keep on increasing to reach maybe something closer to 85% by 2021. So it's of course, a very used platform to do this data traffic. Now, if we look at the various mobile generations which are used to really generate this data traffic, so of course we are talking about 4G plus, 5G, but let's not forget that a lot of this implementation is taking place. But if we look at last year, 2016, the 3G and 3.5G was still the main mobile generation used to generate this mobile data traffic. So of course it's highly increasing, and we do expect to have more of this 4G implementation, and the topic of today to see this what we call 4G plus. Here we are just referring to the technology we're using today that will also remain and be used for sub-6 gigahertz generation. And you could wonder in this plot, so you don't see any 5G. So indeed, if you look at 5G, it has 3 aspects. One aspect is the IoT, so really the global communication among objects with a frequency which is below 1 gigahertz. You would have the sub-6 gigahertz 5G, what we also call the enhancement of the existing technology today, so this 4G plus evolution. And the last aspect of 5G is about millimeter wave, so really high frequencies to go in areas where you have some bandwidth available, and of course then you can use more of this big pipe to really get some data in and out. So if you look at the upcoming years here, we've just indicated, of course, this, the phase of this 5G sub-6 gigahertz that we can anticipate. For the millimeter wave, if you look from a global mobile data traffic point of view, to our knowledge, the 5G millimeter wave is something which is useful for the fixed wireless access technology than really considering the mobile data traffic today. But I'll come back to this point. So let's just have a first glance at this smartphone market evolution. So people are getting anxious a little bit because we used to have a very nice growth among the cell phone worldwide. And since 2013 or 2014, we're seeing the worldwide sales of the cell phone which are plateauing. So here I'm just showing you the distribution. If we look at entry-level phones, feature phones, and smartphones, so you would see that overall, indeed, the overall shipments of cell phone is plateauing, and we have forecast something around 1.4 compound annual growth rate from 2015 to 2021. But maybe let's not be too pessimistic, because the good news is that if you look at the yellow color, so really on the smartphones, we do see quite some dynamism here. So still high shipments being done worldwide for the smartphone, where we anticipate like something which is a bit more than 6% growth from 2015 to 2021. So of course today China is really driving the volume of these systems, and in the future, what could be the next growth relay? So people talk about India a lot. So this could come, for example, by the year 2020. But what is for certain is that China has been very successful in creating an ecosystem to really serve their local domestic markets. And I'm sure Indian players would love to copy this ecosystem to again have some growth in this region. Okay, so worldwide cell phone plateauing, but the good news is that smartphone still has a dynamic growth. Okay. So now let's look at this market for these end systems. So let's try to understand better whose position in this smartphone. So we'll focus on the smartphone only now. So if you look from a volume perspective, that you will see that Samsung is the number one leading company, so has the highest market share with something around 20%. So we anticipate the overall shipment of smartphone last year was something close to 1.4 billion units. Apple would be second, Huawei would be third, with a lot of Chinese players, Oppo, Vivo, Xiaomi, ZTE. Okay, so it's a dynamic market, Samsung getting the majority of the market share. And now if you would look at the same plots, but from a revenue perspective, then of course the picture will look different. We all know Apple is very successful in having some very high-end branding of the systems. So if we look in the market value, we think that the smartphone market was something close to 370 billion last year. And Apple this time would be the leading company with 30% market share, followed by Samsung 20%, Huawei, Oppo, Xiaomi, Vivo, again, a lot of Chinese players, of course, very well positioned. So the main message here, you could consider that if you look at the top three players, they capture 2/3 of the market. So it's highly constructed market, highly captured by these top three players. And Huawei is an interesting company because we do see them as trying to enter really in this high-end, in this premium phone by increasing their standards, their premium positioning. So it's a really interesting company to look at for sure, and try really to compete with these two big ones, which are Apple and Samsung. Okay, so we've looked at the ecosystem of these smartphone players. Now if we go to the cellular technology, so the cell phone, what a great invention, invented in 1973. I wasn't born at that time, but for sure a great invention, invented by Martin Cooper. It took time from this analog system, just the main origin was really this voice, to have voice discussion. It took time to implement, of course, this technology, and I've heard like NTT Docomo was apparently the first infrastructure player to really support this great invention. 2G came around, so a digital, so we switched from an analog to a digital technology, where we could, on top of voicing, then we could use texting, SMS. So this we anticipate around 1990. And then you see all this evolution with the data, with the pre-3G and 3G. So 3G brought the data, so really this internet access. And things are accelerating with video being brought by 4G or pre-4G in 2010, 2012, 2013, depending how you look at it. And what is driving all this enhancement in this mobile generation? Well, video. Video is really the key today, really downloading high-quality video and uploading as well high-quality video to have this exchange with all these social platforms, media, and things like that. So if we summarize, we can say that it takes around 10 years between two cellular generations to transition from one phase to another with some intermediate technologies in between. Now, if we look at 5G, as I said, so there are different areas when we look at 5G. The first one with the sub-6 gigahertz, meaning that we can use more or less the technology we have today. Of course, we have some more standards. We use some more technology tricks like carrier aggregation, multiple input, multiple MIMO. But we can as well tackle this 5G sub-6 gigahertz with the technology we have in place today. And 5G millimeter wave, well, when will that happen? Because this will enable the machine-to-machine communication, really a massive communication among all these objects. You can think about, of course, autonomous vehicles, drones, AR, VR, so a lot of amazing opportunities. So now if we look at the front-end module, so as Stefan explained earlier, what we call the front-end module is very simply all the components which are between the antenna of your system and between the treatment of the information, so like the baseband or the modem, the transceiver doing the analog to digital conversion and vice versa. So we look at the transmission and reception chain, okay? So you need power amplifiers if you are transmitting, low noise amplifier if you are receiving. You need filtering, of course, to select the right frequency at which you will exchange data, and some switches and antenna tuners, like Stefan said, to tune the impedance of your system. Okay? So what you will see is that if you consider this front-end module, you have a huge variety of architectures. So here I just named the big architectures. So you might have heard, of course, the FEMID or the front-end module in duplexer. So the idea is just how do you integrate all these components? They used to be discrete components, and now we are more into an integration approach. So do you integrate the filter or what we call the duplexers? Duplexers just being two filters where you would select or you will isolate the reception from the transmission, okay? So duplexes, we move into quadplexes even, depending on how much carriers we are using to really send the information up to, at the beginning, 2 carriers, 3 carriers, 4 carriers possible today. So you could see triplexer, quadplexes even. So do you integrate them with switches? Then that will be the front-end module in duplexes. Would you integrate your power amplifier with this high-end filtering, these duplexes? Then we would call it the power amplifier in duplexes. Or would you integrate, like Stefan presented, the complete components like the power amplifier, the filter, the switches, all together, what we call the PAM ID or the power amplifier module in duplexes? That's on the main path where you will have the reception and the transmission. Another path I will show you afterwards, where we added a second antenna just for the reception only. Okay, we added a second path, and we'll add more of them in the future. That's what we call the diversity path. And then you find exactly the same, the same principle, integrating filter with switches or low noise amplifiers with filter with switches. Okay, so a lot of various architecture possibilities. That's the main message. And what we see today is that for the high-end cell phone or smartphone integrators, to have very high performance, they are going into a power amplifier module approach, power amplifier module in duplexes, mainly the Apple and the Samsung. Good performance, but then you have a penalty in terms of cost, really customized solutions. While, like Stefan presented, from like more the Chinese players, which are using more a discrete approach, where in fact your focus will be more on the cost than on the performance, then you could tackle, for example, front-end module in duplexes or even discrete components. And that's the old battle that we will see in the future. Each architecture has an advantage in terms of performance and cost, but which one will win? This is something to watch very closely. So to make it very simple, if we look at a diagram schematic of a 3G module, you would have one antenna doing the transmission reception, some switches helping you to select your RF path or your RF line. Then you see the various, of course, power amplifiers. And all this is related to the transceiver to do the analog to digital conversion and the modem to really treat your information. So you could look at it from a very simple perspective, different RF lines, and each of these RF lines with its dedicated power amplifier. It could look, if you look at it, it did look quite simple from a 3G perspective. Now what happened when 4G came in? If you take an example, for example, of the iPhone, so what a great invention, again, created in 2007. At the beginning, if you only look at the total number of bands that your phone was handling, it was handling around 4 different bands, okay? Then what happened in 2012, 2013, when we've seen massive implementation of 4G, so really 4G implementation, LTE bands. So we began at 4 bands and we went up to 30 bands, and nowadays up to 40 or 43 different bands depending where you are located geographically. So you can really see that 4G really brought complexification, a higher number of bands to handle in the same front-end module, and that's where the complexification really started. So now if you would try to do a simple diagram again, and you will see that it's not simple anymore. So you just try to explain how a front-end module, state-of-the-art 4G front-end module would look like today. So we see we are going into higher integration, okay? So we added a second antenna, like I said. So we have the main antenna doing the transmission reception. We added a second antenna on what we call the diversity path. Just because, just to use more of the spectrum, we just slice the information on different carriers. That's what we call the carrier aggregation. Then you send your signal. The signal can be reflected among buildings and things like that. And when your cell phone takes the signal, you might have lost some of the information. So to create a second path, the diversity path, you add more bandwidth possibility, and at the same time you can reconstruct your signal from the main path and the diversity path, and you're sure you haven't lost any information during the transmission or the reception protocol. So we added second antenna, meaning we added more paths, more RF paths, again more components to be implemented. What else do we see is that we are transitioning from, like, here we have some of course, the antenna cross switch, which will isolate the main antenna doing the transmission, reception, and diversity antenna. And then we have some triplexes helping you to select the high bands, the high band areas, the mid band, and the low band. So we are more or less tuning among the different frequencies that we are receiving or transmitting. The same thing on the diversity module. And something else that you will see is that on the diversity path, we've added low noise amplifiers, okay? This low noise amplifier used to be only in the transceiver. As we added a second antenna, okay, we added, again, noise. We want to have a good signal. So we need to amplify a little bit the signal from your second antenna. So we added extra components, this low noise amplifier that you will see on the diversity module. So to make it very simple, with 4G, when 4G came in, a high complexification, we are more today into a high integration, more on the power amplifier in duplexes approach that Apple and Samsung are using to have good performance, but this has some drawbacks in terms of cost. While some other players might not use this power amplifier module in duplexes approach, but more the integrating duplexes only with the switches, for example. So now that we've explained how complex this became, so Stefan showed you some different versions. I just wanted to highlight here the different choices per smartphone manufacturers using different board areas. So, of course, our smartphones are integrating more and more functions. We have less and less space available for the RF board. The phones are getting thinner, so it's a lot of constraints being brought to the system integrators. And you can see the choice of Apple with a high integration. You have a module approach compared to Xiaomi, or you have more discrete elements and more space on the boards, as explained earlier. So if you would open one of these power amplifier module in duplexes, so here we've opened one power amplifier module from Broadcom, the AFM8050, which you can find in the iPhone 7 Plus. It's a mid-band power amplifier module in duplexes. Wow, how complex this is. So this is a system in package, 43 squared millimeters. You would find power amplifiers, which are wire bonded, which first sounded surprising to us, but we're using the wires as an inductance to tune the signal. You would see some filtering, some passives, really taking a lot of space on the different boards. You would see different boards as well. You would see switches and the RFIC, the control mapping. So very highly complex module. Now, if we look at the different players in the ecosystem, so here I was mentioning Broadcom, but who else can supply this integration approach, these power amplifier modules? You would find companies like Qorvo, Murata, Skyworks, Qualcomm with their RF360. So they tried in the past, they haven't been successful, really trying to have a more CMOS approach. But the strategy is changing as they released gallium arsenide power amplifier this year, and they also acquired the filtering division from TDK Epcos. So it's going to be interesting to see what will happen in the future. And you will see that this industry is highly consolidated. You have very few players that can master this front-end module delivery because you need to have all the building blocks in-house, so the switches, the PA-LNA, the filtering, antenna tuning to a lesser extent. So the entry barrier for any new company is quite high. Something maybe to watch in the future is everything related to the cognitive radio. So it's more a software-assisted, digitally assisted radio, which could be an interesting technology maybe for the 5G millimeter waves. But that's a completely disruptive approach. And at the moment, that's not where we are. So now that we've explained more or less these ecosystems in terms of end systems, players, let's look a little bit at market data. Let's look a little bit at some real values. So if we consider this market, these RF components and module markets, so we estimated that in 2016 it was representing around $10 billion, and it will grow to $22.7 billion in 2022, so more than double in 6 years. And it's highly driven by high-end phones. So what we call here high-end phones are these 4G or sub-6 gigahertz phones with an ASP, average selling price, which is higher than $250. Okay. Now, if you would look at this picture and trying to look at this market in terms of various components, here you will see that this high market growth is highly driven by filtering. Filters today represent around 50% of the market, in 2016 at least, and we anticipate they will represent more than 72% of the market in 2020. So a lot of filtering because we are using a lot of different paths, RF paths. We're using more carriers to send and support the data, again meaning more filtering to choose the right frequency. So that's a highly growing area. Now, if you would look in terms of market share, so of course everybody's always asking for market shares. So what we did is that we've looked at all these different power amplifier modules. We've opened them and we've looked at who is supplying the power amplifier, the filtering, the switches, and things like that. And if you do this exercise, again, you will see these 4 big companies I mentioned, so the Broadcom, the Qorvo, Murata, the Skyworks. Broadcom really highly positioned in the high-end value with their very high-end filtering technology, the FBAR. Skyworks supplying almost all the Chinese players. So now let's focus a little bit on the 2 main components that are driving this market, so mainly the power amplifiers and the filtering. And if you would look at this market for the power amplifiers, so we estimated in 2016 it was a little bit below 4 billion. That will be a decreasing market in terms of value because we need more multi-band, multi-mode power amplifiers, meaning a 3G or 4G power amplifier in the future can also handle the signal from the lower end bands. So in terms of volume, we'll have a decreasing market that we'll see also in terms of value. And it's highly driven, again, by the high-end LTE or the 4G power amplifiers, so these multi-mode, multi-band power amplifiers. So in terms of technology, how are they manufactured today? So the main technology is gallium arsenide, and we do see some CMOS power amplifier on the market for the low-end filtering, for the low-end power amplifiers, so the 2G power amplifiers. And we do expect this technology, again, to really offer very nice cost and performance benefits, so to grow higher in this market. But it's not going to be a revolution, it's really an incremental evolution, and we believe gallium arsenide for the sub-6 gigahertz components will still be the dominant technology. Now, if we look at the second component, so the filtering, these highly dynamic markets. So if you look in terms of functions, so we have the 2G, 3G filtering, so more the lower end side, where SO is completely dominating the market. Very nice technology, low cost, very few lithostats. So if you can do filtering with SO, everybody loves SO. Now, if you go to higher filtering functions, so for the standard 4G, so this phone which are below $250, then you would see a mix of SO technology, temperature compensated SO, and BAW. And then now for the advanced filtering, so when we are really going to increase the frequency today, so the main technology is really the BAW, and the FBAR is very well positioned to do the high-end filtering, the carrier aggregation, enable multiplexes, and that's what we expect to see in the future. But if we would look at this picture from a breakdown in terms of technology, as I said, here on the left you have the market in terms of volume, on the right in terms of value. So is highly dominating. It represents more than around 80% of the volume today. We do anticipate that by going to higher frequencies, so today your phone can handle 2.6, 2.7 gigahertz, The next move will be 3.5 gigahertz in the US, 4.5 gigahertz in Japan, so the sub-6 gigahertz frequencies. So there is a strong battle among the filtering companies to really target this high-value filtering. And we anticipate at the moment that FBAR will gain market share in this area, but what we've learned is that Murata has a very nice technology with their incredible high-performance SOE platform, where they really try to push the boundaries of the SOE components. So let's really be careful on that, because it's on production already today, a small volume, more volume expected next year. So it might well be that SOE could maintain its leading position if they succeed to really have a good yield and really increase the volume. So if we conclude, it's again a very dynamic environment with a lot of innovation in terms of architecture. I hope we've demonstrated that. In terms of design type of the transistor, and in terms of materials, a lot of different materials being used. So here we only focused for a matter of time on power amplifier filters, but you could also look at the low noise amplifiers on the switches, and you'll see a lot of different platforms. Gallium arsenide, SOI, CMOS, GaN, not yet for the handphone market, but very piezoelectric substrates, aluminum nitride, scandium aluminum nitride, like Stefan mentioned. So very innovative in terms of materials. And if you would conclude and look at this overall market, as I said, we anticipate it will grow from a 10 billion industry today to a 22.7 billion industry. So again, more than double in 6 years. And filtering, of course, will be the very interesting and driving force in this environment.
All right, thank you all for this interesting data and analysis. We're going to end this webcast with a few questions. So, as already mentioned we will try to also answer questions by email if we don't have the answer right now. So the first questions are for Stefan. Stefan, we have one question, which is, how do you envisage the RF front-end technology evolution in the next few years? Could you comment on that, please?
Yeah. I think there is a different approach depending on which OEM we talk about. We think that Apple or Samsung will maintain their business model, and we will continue with PAMID component. But if we can look at if we look at the low-cost company, even if I didn't consider Huawei as a low-cost company, I think they might change their way to see the future. Maybe they could lay down the PAMID and focus on the FEMID that could become less expensive and a better way to reduce the cost.
Okay. Next question is, will power amplifier module integrated device still be the solution of choice for OEMs? As
I said, considering the cost of the PAMID, we think that could be the choice of expensive OEM like Apple or Samsung. But the other one, LG, Xiaomi, or even Huawei, will focus on lower cost solution.
Okay, and according to you, which filter technologies is the best position for the 4G plus and 5G evolution?
as Claire mentioned, with the high HP SAW filter from Murata, we think that maybe SAW filter is not a complete lost technology in for 4G plus and 5G evolution. Maybe we have a lot to work on, maybe on the design that we can improve to go through the actual limit of the SAW filter that we know, and maybe go through more than 2.6 gigahertz. And the BAW filter, I think, will remain the main component in this filtering technology.
Okay, thank you very much, Stéphane. We have still time for a few questions to Claire. Claire, when do you see the first 5G deployment coming?
Okay, so that's a good question. So that's not a point we've covered here. But true, this 5G. I mean, there are a lot of work being done, a lot of communication. But I must say, in the past year, I've seen a lot of efforts in really bringing this 5G. Of course, it's very active in the US, in the United States. So, okay, you might all be aware of that. But yeah, companies like Verizon, I mean, they're really already implementing 5G. Again, as I mentioned, when we talk about 5G, there are three aspects. One is this massive communication, so for IoT purposes, so frequency below 1 gigahertz. One is the evolution of the 4G, so the sub-6 gigahertz, and that's really where we are today. The next step from where we stand today will be, as I said, this 3.5 gigahertz in the US using the CRBS band, for example, maybe more likely 4.5 gigahertz in Japan, but we do like standards. I mean, and that's apparently will be clarified in the coming years. And this millimeter wave 5G, and that's this millimeter wave 5G for me, where there's a lot of unknown, of course. But as I said, it's a very interesting technology for this fixed wireless infrastructure to start with. And then we see companies like Verizon, AT&T, T-Mobile. Everybody's, I think, trying to get ready also for these Olympic Games in Korea, in Japan. So we see a lot of attraction there. But really for this communication with the mobile phone, that's not something we anticipate before, 2023, 2025? I mean, it's difficult to answer today, but definitely not for tomorrow. More on the infrastructure side for this fixed wireless network first.
All right. Just a last question for Claire. How will this affect the front-end module industry? I mean, the 5G deployment.
Oh, okay. So again, the unknown there, so here, of course, we've discussed about what we can anticipate. The next move, this sub-6 gigahertz, where we'll have more carrier aggregation. We'll have from 1x2 or 2x1 MIMO. We'll go to a 4x4 MIMO with the Apple iPhone 8 apparently being brought to the market in September. Now, if we talk again on 5G, this millimeter wave, as of today, so the limiting technology seems to be filtering, of course, when we move to these very high frequencies. We haven't seen any working solution that can withstand the low cost and the high integration needed for the smartphone integration. Only one player claims to have a solution, so Qualcomm, and that's what I think Stefan tried to explain. Qualcomm claims to have a solution for the 5G millimeter wave using a glass interposer, maybe printing the antenna on one side, having the chipset on the other side. So, I mean, that's a very innovative approach, and that shows how difficult this 5G millimeter wave tackling is in terms of technology. So for sure, we'll see big changes with this millimeter wave. Again, that's not really for today. Even I know, so Qualcomm claims to have this solution and to do some implementation in 2020. It remains to be seen. I mean, it's very complex, and it also will be interesting to look at the architecture we are having today between this power amplifier module in duplexes and this front-end module in duplexes. Which one players will choose, because apparently in terms of performance, yes, this is great, but cost also is important in the equation. So I can only make general answers to that.
All right, thank you very much, Claire. Well, thank you all for listening to the full webcast. We hope you've enjoyed it and found interesting data. As earlier mentioned, we will send you a link to the recorded video, and you can get the material in the material section of the webcast. Thanks a lot for your participation. We hope to see you soon on another webcast or a Yole event. You can visit our web portal i-micronews.com to get further information on RF. Thank you very much and have a nice end of day. Goodbye.